Okay, I think we'll go in and get started. I think a few folks will be joining a little bit late, but I'm looking forward to our times today. As I mentioned on Tuesday, Tuesday is going to be a little bit more focused on lecture, and Thursdays is going to be more focused on us actually let's roll up our sleeves and do some system engineering. And we're going to be doing that mostly with modeling. And so I'll be walking through our tool called Visual Paradigms. But let me go ahead and open up in prayer. I'll give you a synopsis of what is the order of things that we'll be doing today, and then we'll get into it. So, dear Heavenly Father, Lord, I pray that you would be working in the lives of each of the students in this course. Lord, I pray that you would help each of these individuals to become wonderful, well-equipped engineers, that they can be in whatever area, whatever industry that they seek, that, Lord, that you would bless their efforts in that regard. Praying that you would also help them develop character, help them to get a better understanding of Scripture and the theological concepts that we want to be deriving from that, and give them interesting and creative ways for faith integration. In Jesus' precious name, we pray. Amen. Okay, well, we have a lot of interesting material that we're covering in our course, and so this is the cover. Hopefully, everybody has gotten a copy of this textbook by now. System Engineering Principles and Practice. Koskoff, Seymour, Flanagan, and Beamer are the authors. And so this is going to be the primary textbook that we are going to use, as I mentioned. But now when we're getting into Thursdays, when we start to do some model-based system engineering, we'll be using more of the information from this textbook. And I'll be showing you a model a little bit later that one of these authors actually made, and it's available. I'll have to be opening it up with a different tool, the one that I try to mention briefly. We're going to be using Visual Paradigms, but there's also another tool that will be interesting for us to be considering. Then we have the NASA System Engineering Handbook, which is quite excellent. So what we're going to do today is we'll be going over this chapter number 2, talking about the structure of complex systems. And what I'd recommend, if you haven't already, go ahead and download the Visual Paradigms. I'm going to be opening that up and giving you a tour, and also trying to encourage more of a dialogue to be thinking about what it is that you want to be doing for your project and thinking of that concept. And I think with some of our discussions with Visual Paradigms Open, that it'll start to make a little bit more sense. Okay, well, let's get into this structure of complex systems, chapter 2. My intent is to go a little bit faster going through the material in each of the chapter, because there's more detailed recorded lectures that I did over the summer and in the fall that you can take advantage of. And so let me just try and give some of the highlights here, and you can be thinking about this. And so this whole idea of thinking like a systems engineer is an interesting thing that may be a little bit different than what you have experienced. And so this course will help to build upon that. So the need for a system engineer to attain a broad knowledge of the several interacting disciplines involved in the development of a complex system raises a question of how deep that understanding needs to be. And so I annotated this graphic to just give a distinction between a system engineer. So basically it's wide, you have knowledge across many different fields, and actually in a pinch could be a subject matter expert, at least to a degree. But in contrast, the domain, the width of what a subject matter expert is going to be less, but they're going to have a lots and lots in depth, and we'll have a couple graphics that will help to build upon that. In terms of the hierarchy of complex systems may be represented by a hierarchical structure in things, say, like subsystems, components, subcomponents, and parts. And we'll see this in different ways with some of the graphics that I'll show. The domain of the system engineer extends down through the component level and extends across several categories. And so you can be going down to the components, but across a lot of different areas. In contrast, the domain of the design specialist extends from the part level up through the component level, but typically within a single technology or discipline. And so that's what I'm trying to show with this graphic here. And so here is just one way of thinking about that system design hierarchy. You can be thinking of systems, and below systems would be subsystems. Below that would be components, subcomponents, and parts. And so as you're thinking about what you're going to be modeling, you don't want to make things too low here in this hierarchy so that you can get the whole vantage point of what we're going to be getting exposed to with the 9 different views and 9 different ways of how we're capturing system engineering information in SysML. So a system, it could actually have systems below that. It could, maybe you could call this a system of systems. Sometimes that's even a layer above that, and sometimes there's an enterprise even a layer above that. So you need to have communication, information, and stuff like that would be at that top level, and then it starts to have various points below that. And so here is giving us a perspective of the knowledge domains. And so we'll be hearing these terms. So here could be like different domains. And so electronics, electro-optical, software, electromechanical, mechanical, and thermomechanical. And so I'd like to think of a system engineer as like a conductor, is trying to make sure that all of these things are in sync. All of these things are coming together. And so this would be at the component level where we get into this type of designation. Say at a subsystem level, we're a little bit higher. So you can be thinking of signals like in this last chart, like communication signals might be something that would be there. What is the data? How is the data being routed from point A to point B? There needs to be energy sources to make this all happen. And then there's other materials that are required of various sorts to make this all function properly. So for system building blocks are at the level of components and are the basic building block of all the engineering systems, characterized by both functional and physical attributes. And we'll start to get a better sense of these. Functional means, just if you think of it, function. So it's not necessarily exactly how it's going to be laid out, but it's trying to capture what it's meant to be doing. And then a physical is getting into more specifics about a specific instantiation. So folks, each of you are logged in with your computer. You might have a Mac, you might have a PC. And so that would be an example of a layer that's getting down into the physical implementation. Now you can have different processors. You could have maybe an x86 based processor or an ARM processor, for example, with Apple going to Apple Silicon, and it's based on a whole different architecture for the processor. So the functional elements are functional equivalents of components that are categorized into 4 classes of operating medium: the signals, the data, the material, and the energy. And so we saw that on this previous chart here. The signal element, which senses and communicates the information. The data element, which interprets, organizes, and manipulates information. And the material, which provides structure and process material. And finally, the energy, what gives it the resources to actually empower it to be able to do what it's meant to be accomplishing when we think about the system. So this gets into more details, and so I won't go over this in as much detail, but this from the textbook, the process converges onto a set of 23 functional elements, 5 or 6 in each class. And so these are listed in this table. And so we have another related table over here, but here are, first of all, these class of functions of signal, data, material, and energy. And then we get into more specifics, the component level. And so we have the electronics, the electro-optic, the electromechanical, mechanical, thermomechanical, and software. And so we're just having an expansion of this figure that we showed before that to have us think about that in a little bit more detail. So components are physical embodiments of the functional elements. So function at a higher level, physical at a lower level in terms of implementation, which are categorized into 6 classes by materials of construction. And so electronics would be slightly different than thinking of the mechanical. We had an illustration last time when we were having a lecture where it was trying to focus a high level on different views of how you might be thinking of a system. And so you can think like a structure. This would be the mechanical, and it's just affectionately looking at that as an I-beam. And so maybe that's something that might be interesting to give a perspective of what's trying to be considered in that domain. Electrical. So with you folks, either you're an engineer or focusing on electrical engineering or mechanical, and so maybe one or more of these things might be the area where you're going to start to have a little bit more depth. So these are like some career decisions you'll be making. And so do you find yourself wanting to be a system engineer? You're still going to have your home base. And so maybe it's electrical, maybe it's mechanical. And so you're going to have a little bit more depth, but over time, you're going to be building that width. You're going to be able to straddle across a lot of different domains as you're having to deal with these complex systems. System building blocks models can be useful in identifying actions capable of achieving operational outcomes, facilitating functional partitioning and definition, identifying subsystem and component interfaces, and visualizing the physical architecture of the system. And another thing that's important is trying to think about when it's operational, how is it and where is it going to be? So here at APU, we've been doing some work in the CubeSat arena. And so that's going to be in space. And so that's going to be very different than just sitting on your desktop, if you will. And so those are things that need to be thought about. How are the system operators going to be engaging with this? Is there going to be a mechanism for maintenance, housing, and support? What about shipping and getting it into that system environment? What about weather and other physical environments? And what about threats, hostile environments, or things that might be, it has to be playing in? And so thus with a system context diagram, this can be helpful. What are the external entities that it has to be engaging with to be functional? So just to give an example, say like the system is a CubeSat, and so it's going to have to be communicating with the ground for commands. It's going to have to be communicating with users. Or maybe this is a CubeSat system, and so an external entity could be like it needs to be getting position and timing information from GPS. And so it's trying to get that information and it's going to bring it into the system. Your solar panels, it's going to have to be pointing those solar panels in the direction of the sun to be producing energy and storing it in the batteries or using it for real-time operations. So that's just a couple examples. And I know Abby asked me a question about, well, what would be an example of, say, something that she could be doing for her project? And she mentioned an automobile. That's definitely something that would be worthwhile. But I also wanted to have her think in terms of something like a Tesla, where it has all the basic automotive functions, but it's also going a little bit further. How is it going to manage to have an autonomous operation? And so it has to have sensors, it has to have processing of that information in real time. And so it's maybe just a little bit more complexity that might be thought of if you were to envision a system like that. we're going to be getting into use cases first. And so maybe some of these things might be giving you some tips about what you might be putting into a use case diagram. What are the most important things that are characterizing the system that you're trying to develop? And so here we could be thinking of an airplane. And so it has to operate in rain and wind and turbulence, all of those things, and still making it, a relatively speaking, a safe and comfortable ride. And so it also has to be communicating with the ground terminals, the operators, who give them direction on what they're going to be doing. A critical type of activity is the landing, and so you could actually have a separate use case that would be focusing on that. So a flight environment, you could be talking about what would be the actors and the verbs, what are the activities that are going on. You can be talking about a landing environment, a support environment that it needs to be able to, when it's at a terminal, that it can be powered up by local power. It can be refueled even while people are getting on or getting off the plane, or luggage is being put on or taken off. And then to get an idea of the configuration, that passengers are typically on the top and the luggage is down towards the bottom. And you need to have a unique environment for the pilot. And finally, maintenance, having the things accessible and well laid out, so maintenance is going to be easy enough to do. So this starts to get into the whole idea of interfaces and interactions. And so interfaces are a critical system engineering concern. And so this is an example that, say, a subject matter expert is not going to have to deal with, because you're going to have to be thinking about the whole. So these, which affect interactions between components, and can be classified into three categories: connect, isolate, or convert interactions. They require identification, specification, coordination, control. And moreover, test interfaces typically are provided for integration and maintenance. So those are just a couple of things to be thinking about. And well, why don't we think a little bit about the difference between a functional and a physical interface. So here you can be thinking at a fairly high abstraction. And so you can be using this analogy with a plane. And so the ailerons are one of the things that help the plane figure out if it's going to go up or down, or go right or left. And so when you have a control lever, what is it going to mean if you just move it a little bit? Are you going to get some amplification for the actual aileron deflection? And so here could be a functional capturing of that. And then when you get into a physical interaction, it's more detailed. And so you can say an aileron deflection, 3 degrees per degree of stick. And so a small motion of your stick, it's 3 times that dynamic range when you actually have it in the aircraft and the things that are here. So here you can see the ailerons on the wings. And so this would be the thing, how this controller would actually take place. And so as a system engineer, you're not necessarily going to be designing the transmitter, the antenna, or what materials is the aileron going to be built upon, but you're going to be talking about the functions, and then making sure that all of these things work out together, that the interfaces are correct, the information is properly getting passed from point A to point B. So here are just some examples of interface elements. Maybe there's connectors, and so you're trying to get information from point A to point B. Maybe there's isolators, and so you're trying to prevent thermal feed through of heat from one point of a system to another. Or maybe you need to convert things. Maybe you have batteries on a plane and you need to convert it to AC. Or maybe you're on a satellite or a CubeSat and you have like a 28-volt bus, and you need to have things at 5 volts, 12 volts. And so there's various things that need to be converted. So those are a little bit examples of mechanical and electrical types of things, but there's other things that are listed here that come into the area of things that need to be considered. In terms of the complexity of modern systems, there is a fair amount of complexity. And so I know this is a class and we only have a limited amount of time, but I'm trying to give you, say, a bigger picture of what this potentially could be. And hopefully with the work that we're going to be going through in lecture, as well as the hands-on work with doing some modeling, you can get a better sense of what this is. So each system is always part of a larger entity. And that's an interesting point too. There's always a system of systems that can go above what you're thinking about. So at times, this larger entity can be classified as a separate system in itself, which is beyond simply an environment or nature. These situations were referred to as system of systems, and they tend to exhibit several distinct characteristics: operational independence of the individual system, managerial independence of the individual system, geographic distribution. There can be some emergent behavior. If you hadn't thought about these things, how they would work together, that there's going to be some results that are characteristic of that as a new whole. There can be evolutionary development. People get better at knowing how to work with these things together as a unit. There can be self-organization and adaptations. So enterprise system engineering is similar in complexity, but focuses on an organizational level. And so, so we have systems, we can have systems of systems, and then we can have enterprise systems. These are some terms that we're going to be getting some insight into as we progress in the course. And so this just gives you that pyramid that includes these higher levels. And so maybe you're focusing on a system, and maybe for you, it could actually be a subsystem, but from your point of view, that's going to be the highest level. Maybe for your first job, that might be where you're starting. System of systems could be looking at the whole spacecraft, and the enterprise could be, say, like if you're doing something with GPS and 24 or more satellites have to be operational together to form that overall capability. So that was, relatively speaking, a quick survey through chapter 2. The recorded lectures, the textbook, all go into a lot more details. But we got a chance to be thinking about the system building blocks and the interfaces, to be thinking about the hierarchy of complex systems and where a system engineer would fit in that. Thinking about the system building blocks, the system environment, the interface and interactions, and the complexity that's found in modern systems. Okay, well, let me pause to see if there's any comments or questions on what I shared. Maybe I'll just do this. If everybody is okay with that, maybe just give me a thumbs up. People tracking? Okay, good. Thank you, guys. Well, let's go ahead and next let's move in the direction of the sweet spot of what we're trying to do on Thursdays. And so first one I'm going to do is open up visual paradigms, and I have a project already open here. And so we could do a thumbs up again, or just put in the chat if you like, or just go off mute. Did everybody successfully get the visual paradigms installed on their computer? Okay, good, Jonathan. Glad to hear that. How about some other folks? Okay, Abby, good. Nathaniel, Kyle, I just wanted to verify because I can go through some more details on that just to make sure that everybody is up to speed. Okay, well, just in case, Kyle may not be at a place where he can easily respond, but what I put into actually, I think I'm sharing the wrong screen. So let me stop sharing and then reshare. Okay, so this is what visual paradigms looks like. I'm going to talk about that in a minute. But here I put in a link, and I also sent an email within Canvas so that you can easily get to this. So I think you might be able to just download it from here, or you can also just go directly to the website. And so it knows that I'm on a Mac. And so Mac is in this area of transition. I still have an Intel Mac. And so I'll be doing that for a couple years. And so you would pick the right one. And if you have a Windows machine, you could just download that, and that should be relatively straightforward. The thing that you're going to have to do, you'll have to register with an email. But once you've got that, then you'll have this community edition version of Visual Paradigms. And so it is a pretty accessible model-based system engineering tool. For the most part, I've been pretty happy with it. And so that is what we're going to be focusing on for a couple reasons. It's something that's available for free for you all as students, which is an important thing. But it also does all of the things that we would want to be doing for SysML. I'm going to go and close this project. And so this is which, when you first open it up, it will look something like this. And so if you're going to be creating a new project, you would come up with a name. You can just leave this as UML, and you can, that is fine. Then after you have that, there's a couple ways. There's a little caret on the bottom. I know that I have was just working on something earlier today, and so it gives you this shortcut, or you could just go open, and you could just be searching your local file system to find where you put your project. Okay, for today, I'm going to be having this a little bit more as an overview. And so I'm going to go ahead and open up something that I've already put together. And so this is something I've been doing for the last couple of years when I've been teaching this course, and I've been gradually refining something. And so remember, the first thing that you have to be doing is to create a proposal of what you would like to be doing. And so this is still relatively short, but this is giving you a sense of, say, like what I was trying to do. And so this is an APU ECS CubeSat SysML modeling. And so the purpose of this model effort is to explore a top-down systems design for a CubeSat, and it uses something called, and this is a term in system engineering, an object-oriented system engineering method, or OSIM. And so I think you'll be seeing that we'll get hopefully a better sense of what I mean by that as we go through this. So it's going to generate a CubeSat system design utilizing SysML diagrams, and it's going to include a payload. And part of what the trade will be thinking about is considering between a communication and a remote sensing payload. And I also want to get a chance to define key performance requirements. So that's going to be one of that'll be like the major thing that I'm going to be using as something that I'll be having us walk through in class. But I'm also been doing some research in something called neuromorphic computing. And so this is part of the time I will be doing something fresh with this, but this might just give you an idea of, like, for your project proposal, you're going to need something longer than this, at least a good paragraph that's talking about what you want to be doing with your project. And then we want to be thinking about, well, what are we going to be doing in each of these 9 types of diagrams that we will be getting our arms around. And so this is me just trying to flesh out some of those ideas. And so the first one we're going to be doing is looking at use cases. And from those use cases, this is going to be helpful for us as we start to figure out the requirements. And a requirement, to be a requirement, the operative word is it needs to have a something called shall. So the operator shall configure the satellite or something like that. That would be an example on it. Kyle, thank you for letting me know you're working on it. If you do have issues, please let me know, because I want to make sure that you have this, because especially on Thursday, I want to get a chance for us to be doing this real time, that you can be working on your project, on your modeling while we're meeting here. Okay, this doesn't actually happen natively within Visual Paradigms, but in a few minutes, I'll be showing you another tool where it does this by default. So I created some folders to try and organize it in a similar fashion. And so I have this one here. This just gives this an assessment purpose, but there's another kind of a neat thing that I can do where these are just small little icons of a variety of different SysML diagrams that that I've created. And so this is just a way that's useful to have something I could be sharing with you all. So I'm going to be showing you the full-size versions of this, but this just gives you an idea maybe of a trajectory. The first thing we're going to be thinking about is the use cases. And maybe you've heard the term user story. And it can be a narrative. And then you start to convert those types of thoughts into the requirements. And the way that we'll be doing that within SysML, we'll be doing it in a requirements tree, and we'll get to that next. And third, and this is as far as I'll go for our discussion today, we'll be thinking about things in terms of a block diagram. System engineers deal with block diagrams all the time. And so that may be something, if you haven't heard of, that you'll start to see that there is some utility in being knowledgeable about that and starting to use that. Okay, I'm going to go over to the other tool briefly, and then I'll walk through a use diagram, a use case diagram. And so let me just go ahead and this tool has actually had a number of different names, and so I've heard it called NoMagic. Here it's called Magic Systems of Systems Architect, and CATIA is now a part of something called the Dassault Systems. And I've seen a lot of aerospace companies. I've seen the Aerospace Corporation where I worked. NASA and others have used a tool like this. And so this is a enterprise version. And so I finally cracked the nut and I was able to get an academic version of this. It's still not free, but this is something that can cost like tens to hundreds of thousands of dollars to get licenses for this. And so for something a lot lower than that, I was able to get something that I could be using in this class. And so you might recall that one of the authors in our textbook is called this for the SysML textbook is Freudenthal. And so he has done a couple other types of textbooks. And so this is the model that goes along with a different text. Let me see if I can get it to work here. And so this is a textbook called Architecting Spacecraft with SysML. And so this is a model that's freely available on the internet, and I've actually found two others. And so I will be referring to some of the things that are in here. And you can see that it had the same type of a structure, the way that they organize the material in here, plus a lot of other things. And so this is a a tab that shows you the diagrams. And here is just another way that gives us some information about the model. So as a result with these, I'm going to be able to not be starting from scratch, to have some things that I can be sharing with you and get some perspective on this. So if you all have visual paradigms installed, why don't you go ahead and try and create a new project, and we'll start to flesh out a use case diagram. And this will be something that would be useful for us to have a little bit of a conversation. So whatever way you want to do that, if you want to go off mute, if you want to put it in the chat. At this point, do you have a sense of what you would like to be doing for a project? And if you're still kind of unclear, and you could always default to doing something with CubeSats. The last couple of years, I tried to make that as a domain, but that's not necessary. Like Abby was possibly considering doing an automotive system. But you could, if you want, you could be doing it as a CubeSat. And then we have to be thinking about what we're going to consider inside the system. What I had done, I was trying to have people think that the system would be the CubeSat, the ground station, and the mission control. So anybody want to share what they are thinking about they would like to be doing with their modeling in this class? And if you're not sure, just give me an idea. If folks are still struggling with that, why don't you maybe just do a thumbs up if you like, whatever's a way that I can get some feedback on how it's going for you.
I was thinking of doing like missile silos.
Okay. So believe it or not, now Nathaniel's mentioned missile silos, Abby possibly doing something related to automotive capability. First of all, it's not trivial to just come up with an idea. I remember when I first interviewed for the first system engineering and integration company I worked for, and I think I had mentioned this, what he said as we were finishing up with the interview, and he says that systems engineering, instead of having to work harder, you have to think harder. And so you're having to think of the whole complete entity, what it's all about. And that can be pretty overwhelming. And so you're going to potentially experience a little bit of that as we're going through this material and starting to capture what you might want to be working on. I can also chat with you folks individually and help you to see how to flesh this out. So for Abby with an automobile, maybe a Tesla, or there's plenty of other cars that are out there, or for Nathaniel with a missile silo, you probably want to do a little bit of research to get a sense of what exactly that you want to try and create. And so a missile silo, and so you have an operator that can actually open the silo. A maintenance can actually go in and configure or retrofit the missile inside of the silo. And so for this very first one, those are the kind of things that we would want to be thinking about. And so just to give you an idea, so what I did is I did a right click. There's a couple different ways like this. And so I could put in a new actor. I'm not going to keep this, but I'll just so you guys can do this. I'd recommend that you do this in your visual paradigms. And so now I have an actor. And I want to be creating a use case. Okay, so this is a use case. And so this actor wants to have a connection here. And so this is an association with a use case. Uh, there's a couple of shorthand things here, and it actually did that for me. So I want to do an association, and so I didn't name it yet, so I just use the default. And so what this does, it creates a relationship between an actor, and so the controller configures the system. There is something here that I show you that you can also create a system. You can change the color if you want, and so that's what I did. You go to styles and then go to color. So that's the kind of color I used before. And I think if I do this, it'll put it in the systemable case. Yeah, so it's locked into that system. And so here can be the starting of you creating a use case scenario. And I would argue that probably having several of these would be important. And this is going to be a first step for us as we start to figure out what would be the requirements that we're going to derive from this. And so the operator shall configure the missile silo, or the drive that would be for Nathaniel. For Abby, the driver shall control the automobile or drive the automobile. So you see that there's a noun, a verb, and so the driver drives, that would be the verb, and then what it is, the automobile. And so it's fairly simple, but for this first diagram, it's intentionally meant to be simple. So this is like something that you would be using to communicate with a stakeholder or the person that is paying you to be doing whatever it is that you're trying to accomplish with your system. So let me get some feedback. Were folks able to begin to create oh, I think I forgot to tell you one thing. So first of all, let me get rid of this. I didn't tell you how to create a new diagram. So if I wanted to create a new diagram, you click under the diagram palette, and then you click new. So I want to create a use case. You can scroll through this, but there's a lot of them. So then you create a use case diagram. And there are a variety of templates. For our purposes, I would say just go ahead and choose a blank one. Then you want to create a name. If you don't, it will give you a default one. And so this just gives you an idea of how that would work. So let me see, are you guys following what I did? Does that make sense? Okay, good. Got a few people, it seems to be working for you. Let me check some of the other folks, because we're going to be doing some hands-on on Thursdays. So Abby, does that make sense? You tracking? Are you able to? How'd you get the yellow rectangle? Okay. Let me try it a different way. So you also have this palette over here. You have a couple different things. So you're gonna have to make sure you get to the right one. I think it's the default to the top. No. So is it this one? No, this one. I play with this enough, so I may. Okay, it just defaults to that. So this is the system. So that's a system. And here is an actor. It's probably easier just to use this palette. And the way that you do, and then you have a use case, you pop it in there. And then when you just hover over your mouse, you'll see this little thing up here that'll show up. this is how you connect. So if I click on that, and it didn't create anything yet, so you can make an association and it would go to that. You definitely don't want to leave these. You want to make this specific for the system that you're working. Did that help, Abigail?
Yeah, thank you.
Okay, good. Jonathan and Kyle, any comments or questions on that? Is that working for you?
I'm struggling to create the project.
Okay. So let me get rid of this and
Yeah, I'll have to figure this out later.
well, if at all possible, I'm gonna try and help you along that. So let's do there's a couple ways that you can do it. I think you can actually just do here. But we're starting with a use case diagram, so I think technically it would be going over here. I think if I do this, it'll start a new project. Yeah, let me just do it this way. So create a new, call it test. So Jonathan, maybe just follow along here. You can just leave it to the default for UML and then just create a blank project. You see how that works?
Yeah.
Okay, now you have a blank project. And so then you want to go to the diagram tab and then you want to click on new. And you can just click in a letter or two and it would start to show you that. So usually a letter or two is all it's going to take. And then you, with that, create a blank one. And then you got it. Okay,
Oh, okay. Thank you. That helps.
good. There is a learning curve with using a tool like this, and so I'm trying to minimize that for you if I can, and help you to start to see some of the cool stuff that you can start to develop from this. So I'll just go back to Kyle just for a minute. Kyle, anything else you want me to show you? Or if you want to do it on your own, that's perfectly fine, but I'm also trying to give people a leg up for this. Okay, well, Kyle, you can let me know if you're still getting stumped a little bit, and I can try and help out a little bit more. Okay, I'm going to exit out of that. I'm not going to save it. So that's an introduction to the tool that we'll be using, and so let's just have a little bit of a discussion. If anybody wants to be talking about it, I know I've mentioned this once already, but what do you guys want to be modeling and now, or plus I could be helping this out a little bit more next Tuesday and Thursday. Let's just begin to start to flesh this out into specifics. Let's just pretend like you're working for a company and they're going to pay you 6 months or a year to develop a project, but you have to put it into the proposal format that they have given you. And so we had so far, Nathaniel has mentioned doing a missile silo. Other folks are still trying to figure things out. And if you're struggling, if you have an area of interest, just let me know. I see Abigail has a question, so let me go ahead and I'll just run through this. I'll do a blank one. and go to diagrams, go to new. It does remember the last one that you created. So just go with the blank. And so I'll just populate these things quickly. And so what Abby was asking was how to change the color. This is something that took me a little while to figure out, and it's not intuitively obvious. But if you go to the system, and then you click on styles and format, and then click on format. That's how you get there. And then if you wanted to change it to yellow, I personally like using different colors. So let's see if I wanted to change this, it's the same thing, styles and format. So if I wanted to make it green, I could do that. You could even change it for this actor. So maybe I'll make it purple, but there's not too much color that will change, but still that can be a useful distinction. And so maybe I'll call this CubeSat since that's kind of my default. And maybe call this payload. Call this operator. Okay, now go up here. Well, let me just show you what just happened. If you right click and you want to, sorry, if you just go up here and click on this, you want association with a use case. If I just push enter, it's going to just create a new use case. So that's something that you can do if you want. But if I'm going to connect it to an existing one, then I want to go here. It also remembers what you recently chose, and so that's why it's going up here. And then I wanted to click in payloads, so just a couple of letters, it'll find it. And then it has that connection. You can even change the color of the line if you wanted to, and maybe if I wanted to turn that red, I wanted to make it a heavier line, I could do that. So those are also some things that you can be doing, okay? All right, I think for starters,
The generic connector for the line.
I don't understand your question, Nathaniel.
For the line, did you use a generic connector?
Yeah,
Okay.
let's I haven't really gotten into that yet, so let's talk. This is where you get into the syntax that's behind SysML. So this is trying to show an association. This would be a dependency. So these have some specific meanings. A realization. So say we have like something that's more general. And then you have a more specific thing. Maybe you think in terms of classes, you can think of a class as a student, and a more specific would be something as a grad student or undergraduate. But that's actually dealing with classes is slightly a little bit different. You can have like a one entity having an association with another actor. So say if I had this, and I want to do an association with another actor, I'll just do the default, and so it just created another actor. And so maybe that's the operator, and this one might be a tech or something like that. So yeah, but for right now, I was just using what you're calling, Nathaniel, and I think that's reasonable, just calling that the default connector. Okay. All right, well, what I would like to have us by next Thursday is at least some of you have got an idea of what you're thinking about doing. And if you're still would like to have some help, I can show you a couple other models that I have that get into more specifics on a few things. And then let's start to be thinking about how we're going to be fleshing out these use diagrams that are going to be playing that out. And so literally we can have a working lab on Thursdays where you can be starting to do this together as a class and give you a chance to get some on-the-job training, if you will. Okay? So I'm going to, I'm not going to save this, so just close this and are there any other questions about the course or that you would like to have us talk about since we're all together here? You can see where things are due if you just go to the syllabus tab. It'll populate below that. Also, if you go to the assignment tab, it will show you the due dates as well. So those are grouped by category. So for chapter 1, there's a quiz. And so these are on the order of 10 questions. Sometimes they're a little bit less, but it'll give you another way to help you to be navigating through the material. So on Tuesday, we talked about chapter 1. So that would be a helpful way to give you a sense of what's going on there. We have our project proposals, and so that's going to be due. I put that on January 16th. And so these are things that can be resubmitted. So if you just want to be putting something and then have a discussion with me, I'm perfectly fine with that. And if you click on this, it'll give you an idea of what would be the outline. So you want to make sure that you have a title. You want to be talking about what is your mission, what are you trying to accomplish, a summary of what it is going to be doing, what are your goals, have a little bit of a discussion of what you think the resources will be for this class. That is something just to trying to give you some sense in the future. You would have to have this, otherwise they wouldn't even consider funding it. And then finally, what are the expected results? When you get to the end, when you have your final report, you'll be reflecting back on these things. And so you can go ahead and click on this and it'll give you an idea of what is the expectation that you would be including with this. And so for this one, it's going to be a document. And then when we get into the projects, like we were talking about use cases, you want to make sure that you save a copy of that. And you can do that by right-clicking, export. You can export to an image. There's various types of formats, JPEG, a PNG, a TIFF. Something I've recently been introduced to is this SVG, which is kind of a cool thing that you can zoom in and you don't start to lose the fidelity because it makes it into a vectorized version. And so the lines in the text are kept pristine, which is kind of nice. Any other comments or questions? All right, well, next Tuesday, we'll continue along in our journey. And so on next Tuesday, we'll go into the third of 4 chapters that give this foundation. And so this first one, we got a chance to get some idea of what is system engineering in terms of what it means, but also maybe considering if you were interested in system engineering, how you would start to be going down the path in your career starting out and where you would be going in 5, 10, 20 years from there. Here we started to get a chance to be thinking of the structure of complex systems, that there's different layers And so we're gonna be focusing on those higher level layers as we go in the near term. And then next Tuesday, we'll be talking about the development process. And then next Thursday, for the first part of our time, we'll get into thinking about system engineering management. Okay? So with that, I'll stop sharing my screen. And if anybody does have any comments or questions, please reach out. And if you have some things that you would like to be focused on a particular, I'd be glad to do that. I know, Nathan, you've been helping us out with our CubeSat effort and other related things. And so I know you've got a rich canvas of possibilities that you might want to be thinking about. So that would be wonderful. And I look forward to seeing how that comes together. Okay. All right. Well, God bless you all. I hope you have a wonderful day, and I'll look forward to seeing you next Tuesday.
Thank you.
Okay.
Thank you.
There. Care.